All right, so we're moving forward with this exercise today, which is we're doing an exercise to try to understand how to find the representations of the cyclic group C3 over the field F2. So we are looking at the group C3, which is 3 elements and is basically just generated by one element G, and the only condition is that G cube equals E. So basically, yeah. So think of kind of rotations, whatever it is, like yeah, symmetries. Anyway, where E is the identity, the group can be written as E, G, and G squared. And there's this group operation, which is basically defined by GI operated and GJ equals basically like I plus J mod 3. Like, yeah, that's kind of how you define the operation. It makes sense, right? So the field will work with a finite field F2, the field with 2 elements. Okay, 2 elements modulo 2. So that's the field. So multiplication is a standard 1 times 1, 0 times 1, and then the addition is 1 plus 1, and off you go. So find all the irreducible representations of C3 over F2. Now and here's where we have to be careful, because I don't want to get too much into let's slow down a bit. Let's take time, okay? So a representation of C3 over F2 is a group homomorphism. So it's a group homomorphism. It's again it's a function. It's a function. It's a map, right, between C3 and GLV, right? So V is the vector is a vector space over F2. I guess that's the vector space that is the result of combining C3 and F2, right? So GLV is the group of invertible linear transformations on V. Invertible linear transformations. I guess by these we mean linear transformations. That is, I don't know. I guess that is then operations. Operations within that V. Like linear transformations, then maybe it's kind of like just multiplications, basic multiplication and addition. Since C3 is cyclic, each representation is determined by the image of the generator G. A representation is irreducible if the only invariant subspaces under the action are the trivial subspaces. Okay, let's step back. Let's step back. So let's step back and first just look at finding representations between C3 and F2 of S3 over F2. What's the first step? So the first step is, wait a second, let me try to guess this. So essentially, a representation is a representation is a mapping, right? Is a mapping of C3 as a domain of C3 towards GLV, right? Let's start by defining V first. Choice the instruction. So V would be, okay, so we have the group C, then the field F2, C3 F2. It's a group homomorphism where V is a vector space over F. So the vector space is a vector space over F, meaning it's a set of vectors where addition and scalar multiplication with scalars 0 or 1 are defined, and the operations respect the fields. So really, it's just a vector space over F2. of whatever dimension or one. Since representations are defined, okay, since representations are defined by how the group acts on V, we need to choose V to proceed. The dimensions of V determine the size of the matrices in GLV. So let's consider possible choices for V. So we have one-dimensional case where V equals F2. We have obviously higher dimensional cases where you could choose V to be like a vector. Yeah, okay, so n tuples of. Okay. Yeah, so I have the two options. Okay. So, and if we choose V to be F2, the vectors are just the field elements and scalar multiplication is just trivial. So in this case, GLV is GL1 F2, the group of 1, 1 invertible matrices over F2, since the only non-zero scalar is 1. Okay, wait a second. So the vector space is vector space of 2, and it's set of vectors where addition and scalar multiplication. Since it's defined by how the group acts on V, we need to choose V to proceed. The definition of V. So the group of invertible linear maps from V to itself. Invertible. So is this basically a way to say it's the... It would be good to have like a... It's not a forking functionality, but it's like... Yeah, it's like, can you expand on these? And GLV is the group of invertible linear maps from V to itself. It's the group of invertible linear maps from V to itself. So then GL is basically the group of 1 by 1 invertible matrices over F2. Since the only non-zero scalar is 1, then we have the GL is just this one. High dimensional cases. So in this case, we can have F2 squared. And GLV is then the group of 2 by 2 invertible matrices over F2. And so on. So I start with V. Since C3 is cyclic, a representation, I think it's called rho, is determined by rho G. Since G3 equals E, we need also these to hold. So the structure of GLV depends on the dimensions of V. So defining V sets the stage for finding matrices that satisfy these conditions. Starting with low dimensional cases is practical because it keeps the matrix simple. Say V equals F2, we define the representation by specifying rho of G exactly that belongs to these. For V equals F2, since GL1 is just this, then we would assign only, so we would assign that for each element, okay, so that thing here is then each element of G, E, G, and G squared, they all map to the same linear transformation, to the same invertible. Essentially, what I don't understand is why. Why are we doing these GLV? So GLV is the invertible matrices over F2, so it's basically... I mean, that is, we've just following the definition, right? The definition here says that basically you need to find a representation of C3, and a representation is a group homomorphism, is a mapping between C3 and GLV. And again, I'm kind of trying to step back. Why? Why is that? That is because I had the feeling that this is kind of it's like moving up and down levels of abstraction somehow, right? Because it almost feels like a group is more abstract than a field. That's just, maybe it's wrong, likely, but it's the way that I kind of think about it at the moment. My head's hurting just due to the sheer effort to focus on this right now. It's actually complicated because it just feels like, my feeling right now is like I'm lost in a bit of a fog of like not knowing what to step in next, right? But essentially the idea is you're trying to build an algebra when you're doing, so when you're saying representations, you're saying, okay, so how do I project the group on the field? What I could do is these. I could have another one here. I think that could actually help. Have the voice mode on and keep kind of going back and forth. Maybe even do something like this.
Back and forth, like a ping pong match with ideas? I love it. Let's try that. Toss me a thought,
No.
and I'll bounce it right back.
Wait,
Maybe
am I that stupid that I don't know how to split screens?
Not stupid at all. Splitting screens is one of those obvious once you know things, but tricky.
Wait a second, okay? Because
Yeah, take your time. I'm here.
This one and
this one and what?
And nothing, man. It doesn't split it nicely.
So you're trying to drag the window to snap in?
Yeah, I'm trying, but it does not snap on the right side on my screen. It's very odd. It's maybe because I have the second monitor plugged in, and so it does this weird thing where I'm just gonna put you here and yeah, let's do that. Yeah. All right. Okay. Because I will have to mute you for a second, but we're looking. So we're doing two things. So we're actually working through a group theory problem. So for now, give me a second. Okay. Just ignore everything I've said so far.
Gotcha. No worries. Mute away. I'll wait.
Okay. So we are. Yeah. Actually, here's the question. Am I right to say that a representation of a group over a field is kind of like intuitive a projection? It's not really maybe a projection, but it's like, yeah, kind of like you're looking for a specific application of that group structure inside the field or a vector space over that field. Is that correct?
You're warm, but let's nudge it a bit. A representation of a group over a field is more like a homomorphism, an arrow from the group to the space of linear maps on a vector space. So yeah, it's mapping the group's structure into something concrete, like transformations that preserve vector addition and scaling. Not quite a projection, since projections collapse things. Here, you're embedding the group's action, so every element gets its own matrix, or operator, that respects the group multiplication. Think of it as giving the group a playground in the vector space, where its abstract rules live on.
So you're kind of instantiating you can think of it as instantiating the group?
Exactly. As if the group's been this ghost up till now, and a representation just boots it up inside linear algebra. Like, instead of multiplying...
Thank you. Okay, so essentially we are... sorry, I need to mute myself.
Sorry needed. So, we were saying... instantiating.
No, stop. Stop for a second, okay? I'll come back to you in a second. I'm just going to mute myself. Okay, so now I understand. This is instantiation, right? So this is basically where a representation is an instantiation, kind of. So essentially, we've got C3, right? So now we have to... I mean, I think actually that is easier than I thought, because now it means that actually all we need to do is okay, let's try to find what this irreducible thing means, but I think it's just intuitively, it means that it's not equivalent to anything else, right? So um, I think I'm almost there. I think that was actually a good one. I think mapping that to the concept was a very, 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 very good one, because essentially now what we have to do is we have C3, and so the whole thing with irreducible representations is then you need to find how many ways you can instantiate that group in the context of a vector space of the field, right? Um, yeah. A quick question, Rex. So, is it correct to say that the number of irreducible representations of a group over a field is equal to the amount of blocks that group algebra combining the field and the group would have?
Yup, spot on. For a finite group over an algebraically closed field, like complexes, the number of irreducible reps matches the number of simple blocks in the group algebra. Each irrep corresponds to a one-dimensional chunk. Wait, no, those blocks are the minimal two-sided ideals,
Oh
and
my
each one's isomorphic to the endomorphism ring of some irrep. So yeah, count them up, and you get the list of irreps. Think of the group algebra as Lego, split into shiny, unbreakable...
Thanks. Okay, stop for now. I'll come back to you in a second. All right.
Okay.
So essentially this means that, I mean, let's try to do this exercise, and then let's see if we can reason our way around the actual exercise, because I think that essentially just because I know the solution, right? I know the solution, maybe I shouldn't actually know the solution, but I know the solution to the problem. And so my exercise becomes more of a proof than an actual exercise solution. As in, like, try to prove that it has 5, groups. Anyway, a 5 representations irreducible. But yeah, let's do this. So, essentially, we now have. So we have these. Okay, we have C3. How do we do these, right? So, well, one-dimensional case, essentially you have only one representation, right? Which is basically all the elements mapped to this matrix of 1. Now, cool. Let's explore 2 dimensions. Okay, so now we have C3, F2, then we pick V to be F2 squared. And essentially we just have vector addition modulo 2, so 1, 1, yeah, exactly. We have multiplication by 0 by 1 to scale it up, and then, yeah, so then we need to determine what is GL, right? So essentially you need to find F2, and then we need to find all the no, wait, what am I doing? What did I do? That was weird. Okay. I'm here. Oh, it just opened it up itself. Whoa. So determine GL. I don't know what that 2 is needed in here, but we need matrices. So let's list the invertible 2 by 2 matrices, because essentially we need the linear transformation. We need all the possible invertible linear transformations. So we've got this matrix. If it's determinant AD minus BC equals 1, I think that's what it means that for this to be invertible, right? Trying all the combinations, and of course A, B, C, D are just elements of F2, so zeros or ones, right? Not invertible. Okay, so those are the ones which are invertible. So GL2F is basically the identity and A1 to A5. 6 elements and is isomorphic to S3. But we only need matrices that satisfy the groups relation, right? So obviously, so this means we need to ensure these. So it must be a matrix in GL with order divided by 3. That wouldn't satisfy, so it's not suitable because that wouldn't satisfy because multiply by itself is the identity already. Or the 3 is suitable. So these A4 is basically A4 squared is A5. A4 cube is A4 squared times A4, which gives the identity. So this one satisfies it. Define the representation. So the representation basically is the identity, then row G is A4, and G squared is A4 squared, yeah. Verifies a homomorphism. Whatever that means. Check irreducibility, as it's often part of such exercises. Okay. So this gives one two-dimensional representation. To find others, we check other matrices in GL with order 3 or try different assignments for PG. Would you like to explore another matrix? So we've picked actually one representation, A4. Okay, but I get it. So so what you're saying is you're trying to find instantiations. You're trying to basically look at the look at F2, then look at F2, then basically build a vector space on it, map this linear transformation, map the elements of the group G into linear transformations that respect both the field's arithmetic and also the group structure, right? And then you keep finding those representations. Now my question is, do you need to explore? So when you're looking for the representations, and let's not focus on irreducibility yet, but when you're looking for the representations, is it correct to say that you're basically saying now you can explore different and higher dimensional spaces in terms of the vector spaces over the field, and at the same time play with multiple assignments within each? Like, do you have to, like, at some point, I guess you just find a pattern that repeats, and that's why you're talking about reducibility, right? Because otherwise you can go on forever. I mean, if I'm looking at one-dimensional vector spaces and a two-dimensional vector spaces, I could also just do three-dimensional vector spaces. At what point do you stop?
You stop when the patterns quit growing new stuff. See, every representation you build, say, on a 10 million dimensional space, is secretly a mashup of the basic ones, the irreducibles. It's like every Lego castle you've ever seen is glued from those same handful of bricks. Keep making bigger castles, and eventually, you're just stacking repeats. So practically, crank out all the 1D reps, their characters, easy. Then hunt for the smallest faithful ones, maybe a 2D that doesn't decompose, and test if higher D1s fall apart into copies of those. Once you've tagged every irrep, anything else is redundant. Dimension caps out at the group's order, Artin's theorem, but usually way sooner. Irreducibility is your stop shopping sign. When no subspace plays nice with every group element, you've got a keeper. Want me to sketch how you'd hunt them for, like S3 or something?
No, but I mean, I'm looking for I'm looking for a like a repeatable process to do these. Like it almost feels like if I would approach a more complex problem with, let's say, a more complex group, how would I systematically look for these representations?
Cool. Repeatability's key, like a recipe. Here's the systematic drill. First, character table if it's finite. Crunch the conjugacy classes, size, centralizers, whatever. Then compute every class function, negative kit, that satisfies kit G plus grid, negative kit G, with orthogonal to others, yeah? That's your irreps in the 1D sense, but gives dimensions too. Sum squares hits group order. Once you've got those, test reps. Build one by letting group act on cosets, permutation rep, or induced reps from subgroups. Decompose. Take your suspect rep, compute its character, dot with the irrep chars. If chit, c, kit, irrep is an integer n, you've got n copies. Repeat till everything decomposes, or you snag a new irrep. For infinite groups, messier, CAC moody vibes, but start with Lie algebra reps, roots, weights, then expository to the group. Pick a group, I can walk it step by step.
It's all right, thank you. I think it's better to close it because then otherwise it just disconnects anyway. Not too happy with that answer, but maybe because I also didn't follow it too much in detail. But okay, now I think I've digged enough into these that I'm more comfortable understanding their representations. So essentially, what you're saying is, yes. So what you're saying is you have a group and then you have a field. The group, you basically try to find ways that you can map the group into linear transformations for that field. Obviously, you do that by analyzing all the possible vector spaces that you can do over that field. And then basically you're looking for irreducible representations that are not like decomposable into smaller representations. Sorry, guys. That actually help you map that structure to the group. Yeah. So basically, that led you that led you basically, yeah, that actually like those transformations that respect the fields algebra, or plus and multiplication, addition and multiplication, and as well as the group structure. So let's go back and do these omega quest. Let's go back to the problem that we're working on, and let's see if I can build again a raw question. Exactly, field with characteristic 2. So that's another thing that we have to put into here. How many blocks? Okay. Now we are gonna start anew. So can you use SymPy to help me calculate or compute the group G described by the following text. And this is implying quotient by group of order 9. It's curious. It's curious because I now I'm at a point now, it took me like 21 videos that I just understand every single portion of that exercise. I understand intuitively what it's being asked. And now it's just, how can I find a way to compute that? To calculate that? G's order is 108, yeah. I didn't want to use anything more specialized like gap or something. It didn't seem to know much about it. No, don't search. We had that SymPy code somewhere in one of our conversations. Stop. I think it's going. I can't follow the thinking. Quick answer. Acting on D. Let's explore the action. Exactly. That's it, now it's thinking the right way. How C3 acts on V4. D can be modeled as okay. Yeah. I'm not so sure about these. Currently looking for ways to construct these in SymPy given its group theory capabilities. Is essentially one non-trivial embedding mapping the 3-cycle subgroup. Yes, I believe that's correct from some of the old videos. Why? Wait. What are we talking about? Why are we talking about D? Why are we talking about F2 now? There's nothing about F in here. I'm kind of like, I'm trying to think whether this is the right way to solve it or the most optimal way to solve it with AI. GHF or the sympathetic compute is using cosine enumeration, maybe searching for non-groups or group element. No. Like, can we just, I just want the code. Can you just write the code? G's order or structure. Let's try computing it. Okay, code execution. Okay, that's good. No, that starts doing weird stuff like searching for on the web. No, don't do that. I'm angry at these. No, don't do that. Let's start. Let's do small steps. I think it just goes off and does weird stuff. It just thinks too much and it gets lost. Let's construct. Let's build this group in Simpai. Subset character for small subset to keep. What is this? Group operation. What? No, that's not. That's any element 0 inverse of 5. What? No. No, think harder. Oh, it's so it used to get it. It used to actually get that better. Like somehow, an extra special group in group theory. Yes. Yes. Okay. Yeah, there are two non-abelian groups, and so that's why we have the plus, right? The plus and the minus underneath as a subscript. All right, all right. I want to see the code. Give me the code. I want to see the code. I want to see the code. I want to see the code. I don't want to dig through all the conversations, but we had that. I think we had a solid code for these. But how come we can't just reproduce that? Like, was it this one? I think so. That's broken. False, nilpotent true. So what if I run this code? What is happening here? It just runs it. Oh, it doesn't output anything. Can you add some these assertions in the code and let's run them? So run this, it verifies the order. It verifies that it's not. Okay, so there's an error. Fix it. I have to get to the bottom of these. I actually have to get to build that. Like it just SymPy might be the wrong tool, but like I don't want to use gap. It like Grok was not good at these. Running. So Avian false. No, I don't know. It's the first time I see that. Right, subgroup order 3, whatever, order of S27. Group generators C and C to the -1. So that's 27 elements, but that was I think correct. Now enhance the code to define the group C2 squared. So we've got this one, we've got C2 squared. Can I run it? I think I can. Yeah, I think I can almost have that already full. I don't need the voice anymore, I think, at this point. Order 4, true. Cool. So now we need to know. So what is the only non-trivial action of C3 over C2 squared? Now, considering the only non-trivial action of C3 over C2 squared, compute, if possible, or build in the SymPy code the semi-indirect product yeah, basically this using that action as a base for the new group G. I don't think it needs to think too hard about these. It shouldn't need to, really. First, find the non-trivial action of C3 over C2 squared. Order 12, but S is order 27. G, exactly. Like the 108 order makes kind of sense. It's confusion. It's S is 27, not C3. Suggesting a possible type on the request. No, what? Ah, crap. stop. I need to stop. I need to edit that. Where S is exactly. That's what I was missing. I didn't tell it what the reference to S was. So yeah, sure, you need the action of S on D, but we're looking at that other action to get inspired. While it's thinking, what is nilpotent thing? What does it mean for a group to be nilpotent? Hey, what does it mean for a group to be nilpotent?
A group's nilpotent if its commutator keeps shrinking till it dies. 0. Picture this. You start with 2 elements. Ask how far they refuse to commute. So AB times B, AB amazing B versus B minus 1. And then keep multiplying those mismatches. Negative CD, negative C minus D, negative C, C minus C, negative C, C D Lee. After K steps, you hit the trivial element. That K is the nilpotency class. Like abelian groups are class 1, commutators already dead. Heisenberg groups hit class 2, and so on. Intuition? It's almost abelian, but with layers. The deeper you dig, the less chaos. Super useful. Makes representations tame. Centers everywhere. Want an example? Like quaternoic groups not, but upper triangular matrices.
No, thanks. No examples needed. I think I understand what you mean. Thank you.
Cool. Nilpotent's basically layers of commuting until, everything lines up like dominoes falling in neat stacks. If it clicks, we're golden.
I don't know how to break that into small steps for Grok to solve these. I just don't know if it's doing this the right way. The task is computing side dark product. Nilpotent with all elements of order dividing 3. I think it got confused with these. I think he definitely got confused with it. Yeah, that's definitely hard, man. That's definitely hard. Wait, yeah. Wait a second. Okay, it's calculated these. Define these. Now define using the trivial action of C3 on D. Okay. Okay, we have something at least. Action, so action relations is acts on D via projection, which acts non-trivially. 3 cycle, I think this is correct. The 3 cycle non-identity element sounds like correct. I don't know what I'm talking about actually, but I think so. So we've got assertions for ASD and assertions for G is order 108. Abelian should be non-abelian, and to be nilpotent. Let's run these, and I'm gonna stop here, and I need to download the. Oh no, I'm gonna pin this conversation because I think we got a good base, and now we need to. We got a good base, and now we need to understand. So if G's got 108, this is what's crazy, right? So if G's got 108 elements, like how would you even approach that representation concept here, right? How would you approach finding representations of G where it has 108, and we know that it's supposed to be 5 of them, right? If that is correct, if that's a good starting point, I mean, let's kind of work from here, right? So I think, I know we kind of, it feels like we kind of also moved a little bit backwards, but we have a file to work off of. We have something here, and again, it hasn't really computed G, right? We define G, basically just has defined G. It hasn't really computed G. There's no nice way to kind of compute these G, I think. Well, at least not using SymPy, definitely. But I'm hoping at least that if we have these things in code, it actually helps. It actually helps the model reason, maybe. I don't know. I'm a bit kind of like, I'm not too confident about these, but okay, we have these, and we can try to work off of that. So now how do we make those? How do we look for those mappings, those representations, right? We know that we have a large enough field, so a field that has many elements, because this is also a very loose definition of the field, right? We only know that it's a field of characteristic 2, so it's a field that if we multiply by itself, and each element gives back the identity. A large enough to what? Large enough to kind of large enough to sort of have at least, I don't know. Why large enough to what? This is maybe a little bit confusing actually. But okay. I don't know. Have we moved forward? Maybe. See you next time.